Hello everyone, welcome to Controls Analysis and Design. For this problem we're going to be going over steady state error for a given set of inputs. I'm going to explain this in very finite detail, so it's going to be a pretty long video. If there's anything you know, just go ahead and skip ahead and you'll be able to get to the next section that may be more helpful to you. So what we'll be looking at are these three inputs going into this system. So this is the G that we're using. So the first thing we're going to start out with is defining what kind of type of system this is. And if you've read the book, or if you have the Norman Nice book of Control System Engineering, what you have is this table right here of the three different kinds of inputs. So you have a step input, a ramp input, and a parabola. And you can see, hopefully you can see, this is 1 over s, 1 over s squared, and 1 over s cubed. So constant position, constant velocity, constant acceleration. So you should be able to have this chart around so you know what you're doing and kind of what they mean. So looking at each one of these, the way you determine what kind of inputs these are basically by the variables, or the variables that they're using in each one of these. So in this case, this one doesn't have a t in it. So if you take the Laplace transform of it, you're going to end up with 30 over s, taking the Laplace transform of this value right here. And since it's a 30 over s, that translates from the 1 over s, so this is a step input. Just how to identify these. Again, and then taking the Laplace transform of this one, well, you're going to get 70 over s squared, or over t squared. I'm going to change these t's to s's just so I can understand it clearer within relation to this. But you can say 70 over t squared and it still means the same thing. And then for this one, taking the Laplace transform, oh, sorry, this one's a ramp, I forgot to say, because it's a number over s squared. Now looking at this one, taking the Laplace transform of this, you will end up with 162 over s squared. Now the 162, again, you're going to have to look at your Laplace tables if you don't know where that came from, but you end up with 2 times 81 over s cubed. Sorry. You'll not find that in the Laplace table. S cubed, s to the 3 right there. And this is a parabolic input. Parabolic input. And these will be important when we go back to the tables again here in a minute. Looking at the transfer function, you want to determine what type of the system is totally, so you can determine what is going on. And in order to do that, you need to look at this table. This is table 7.2, where all the different inputs and system types are defined. This one goes up to type 2. You shouldn't have to do anything larger than that inside your class, but in case you do, it just continues on with the example here. Try to find this table, relationships between input system types, static error constants, and steady state errors for steady state analysis. But you can see the type are type 0, type 1, and type 2. Each type is defined by the number of poles. Type number is equal to the number of poles at the origin in the forward branch of the system. So this is the forward branch right here, this little chunk right here. This is the feedback branch. We're going to ignore it in defining type. So all we have is g of s. So we're looking at this function to find out what the type is. And a 0 at the origin would be a lone s out here somewhere without anything added. Because this 0 is at negative 24, because this would make this go to 0. And this 0 is whatever the poles are for this quadratic equation right here. But I'm not going to solve that. So we have no poles at the origin here, so this is going to be a type 0 system. So a type 0 system is what we're working with. So that's going to define what values and equations we use from that chart that I showed just a second ago. A type 1 system would be something like k over s. G of s is equal to. Because right here, if you put in 0, well, that's the origin, and you have one pole at the origin, so you have a type 1 system. Okay, so moving on here. Actually doing the calculations. So now that we know we have a type 0 system, and for number 1, we have a step input. What you do is you go over here and you look at the formula and you see it's 1 over 1 plus Kp is the steady state error. And you can just focus on these for a second here. We're going to ignore this just for a minute. So 1 over 1 plus Kp. So 1 over 1 plus Kp will equal the error at infinity. The reason this is set up like this is because at infinity the system is at steady state. Basically, if you're looking at the system, it's going like this, and then it fizzles out, and it's come to its final value wherever it is, way out here at infinity. So that's why we set it up like that. So how do we find this Kp? Kp, again, has another formula associated with it based on limits. So Kp is equal to the limit as s goes to 0 of g of s. So we're using this transfer function up here again. This is for a unity feedback system. You're looking at the forward loop. So the limit of the transfer function as it goes to 0. You don't have to solve this loop or anything else. The unity feedback loop is a hint that all we have to do is focus on this. So in order to do this, limit as s goes to 0. Well, looking at this function up here, this is going to equal 500 over 0 plus 24 times 0 plus 0 plus 14. And so we've got 24 times 14 over 500. This is going to equal, excuse me, 500 equal to 1.49. So that's our Kp. You take the limit of g of s. Now you're going to wonder how this changes for ramps, and we'll get to that in a second. But just let me finish this. So our steady state error, e of infinity, is equal to excuse me, 30 over 70. Oh, no, sorry. No, math is wrong. 30 over 1 plus Kp. Now you're going to ask, well, where did this 30 come from, Gabe? The 30 comes from the numerator of your input. So in solving this equation, Kp, this is the equation you end up with, but in order to make this legitimate, this equation is for a 1 over s system. But if you have a 10 over s system, then this numerator changes to 10 also. And in our case, if you have a 30 over s system, as we do up here, this is the input, then the numerator changes to 30. And you have to remember that. It's something that's really easy to forget, but you got to make sure that you keep the numbers going all the way through. Alright, so doing this, we end up with 30 over 1 plus 1.49 coming from here. And doing the calculation for that, it's 12.04 is your steady state error. Error. So, that's for our step input. Now, we're going to go on to a ramp input, number 2, and we have an input of 70 over s squared, remember, ramp input. I'll mark this down so it's a little clearer. And looking at our table again, for a type 0 system, okay, this is, I'm going to step back and make another point. Right here in this chart, you see for step input of a type 0 system, Kp is equal to a constant. That's what we got over here. When we found Kp, we found that it was equal to some number, a constant. In this next part, we're going to find the Kp to be equal to something else. For a ramp input of type 0, Kv is equal to 0. So by the table, we're able to see that Kv is equal to 0. Kv equal to 0. But the equation for steady state error is 1 over Kv. So this is what we're looking for E of infinity. But when we do our limit system, we should end up with Kv equal to 0. This is really handy because if you memorize this table, you can eliminate this limit, which is really handy because this limit can cause you problems in the future with what I'm about to show you. Because in finding Kv with this case, Kv is equal to the limit of s of g of s as s goes to 0. So as you can see here, I've added in another s. And this is something you have to remember. With a ramp, you add in another s when you're taking this limit. And if you do this, well, then you end up with, what is it? Excuse me. You'll end up with infinity because you've got 0 over a number, which is basically infinity. Well, no, wait, sorry. You'll end up equal to 0. I can't do basic math. If you have a 0 in the numerator, you're going to get a 0, no matter what's in the denominator. I was getting ahead of myself. But if you put the 0 back over here into the steady state formula, then you get 1 over 0 going to 0. This is equal to infinity, basically. Technically that's not true, but in steady state error, you're going towards infinity, so you're going towards 0, so this is going towards infinity. That's how this works. Normally this is undefined, but in controls we consider 0 in the numerator as infinity. So, and if we look at the table again, if you look at the error in this column, we have an error of infinity for a ramp input of a type 0 system, which is what we just got. So the table should match up with your calculations. If you memorize the table, then when you say, oh, ramp input, one other error in here. This is 70 over 0, kV. We have an input of 70 over S, so this is 70 over kV. So 70 over 0. But if you memorize this table, you could have looked at this and said, ramp input, oh, I have a type 0 system. The error is going to be infinity. And you're done. You don't even have to do this math. And you can say, by table, it is infinity. So I'm going to do one more example here. The third input, which is the 81t squared up here, which is 162 over s cubed. If you want to, from the table, you have to memorize these formulas or you have the table available to you. So 1 over Ka is the formula for the steady state error. So 1 over Ka is equal to E of infinity. But in this case we have 162, so 162 over Ka is equal to E of infinity. And then Ka is equal to the limit as s goes to 0, get this in focus here, of s squared of g of s. As you can see, we added yet another s into this limit. So when you do that, you're going to end up with equal to 0 over a number of some kind, because right over here we've got s squared, which is a 0 times 500, so you're always going to get a 0, and then we don't care what's in the bottom, but you've got a 0 plus 24, and then another 0 plus 14, and that's how you get over a number. So then, which is equal to 0, so you go ahead and put Ka back into here, and you end up with 162 over Ka, which is equal to E of infinity equal to infinity again. And again, also, if you had looked at the table over here for type 0 system with a parabolic input, steady state error is infinity. And Ka is equal to 0. So right there in the table, you have the answer to everything you need. You don't even have to memorize the K's. The only thing you have to know is basically these values right here. The infinity, constant, 1 over K, 1 minus Kp. If you're looking for the constant input, which we had to do up here, you do have to know these formulas. But if you're able to find out that, oh, I have a ramp input and it's type 0, oh, it's automatically infinity, and you're done. You don't have to do any math. So it's really, really important and great if you can memorize this table. If you don't want to memorize, well, then you have to memorize this formula, this formula, this formula, or make a trick to remember it. And then you also still have to memorize this formula, and this formula, and this formula, and everything else. So it makes it much simpler, I think, to just know the table or get your professor to give it to you in a quiz. So that gives you a basic rundown of steady state error. I should be doing more videos, so you can check those out if you want more.